For our project, we used a TI microcontroller. So we are also using TI's Code Composer Studio to write our code. In addition to this, we use MCASP, which is the multi-channel audio serial port designed by Texas Instruments. The MCASP fetches samples from the audio codec and writes them to an input buffer called the RX buffer. Once that buffer has been filled fully, the audio task that we wrote will then be able to perform. Once that's done performing, the output buffer, also called the TX buffer, will be filled. Once that buffer has been filled, MCASP outputs the buffer to the audio codec, which then outputs it to the speaker. In our code, we first check the GPIO polling function, and then we go on to check if we want to output silence or not. If we don't want to output silence, then we will invert the input and pass it to the output using this line here. But if we do want to output silence, then we will throw zeros to the output. And if this is the case, we will also be doing this for roughly 5 seconds. Here we have the frequency detection code working on 3 amplitude data points. We first check if it's less than 200,000, and that signals that we're ready to detect a new peak. 200,000 is also the range that we're calling too little and basically noise that we would like to ignore. This if statement here checks if the values we are looking at dictate a peak, and if it does, then we will increase our peak counter. Once that is done, we can then calculate the estimate frequency based off the peaks, the sample rate, and the array size. Once that's done, we use this if statement here to effectively create our low pass and high pass filter. We found that the frequencies of 150 Hertz and 1250 Hertz work well. This last line here is then the mem copy that transfers the data from the input buffer to the output buffer. Here we have our GPIO polling function. We are reading from pins 4 and 5. Our if statements first check if our GPIO reads a high value, if we have our push button detection flag set low, and if we are within our range of volume between 0 and 100. If this is the case, we can modify our volume using this set volume function. Once that is done, we indicate that we have been activated, our push button has been pressed, and then we also write to an LED to clearly indicate visually that we have modified the volume. Once the buttons are released, we set the flag down to 0, and we also set the LEDs to 0 to indicate that we can modify the volume once again.
For this portion of our project, we decided to create a volume tuner. This was created by using an Android application in which the user has an ease of control of the volume. Simply increase or decreases the volume in respect to how far or how much the noise pollution is affecting them. So they're able to tune that for however close or far away they are from that sound source.
Okay, so I'm going to be going over why we picked which hardware we picked for our project. The microcontroller we picked was the Texas Instruments TMDS LCDK 6748. We picked this microcontroller for a few reasons. One of the reasons was just a pure recommendation from Professor Cottle for the architecture. Another reason was the budget considerations for our project. We didn't want to spend too much money. The main reason, though, was because it's a DSP-centric processing unit for real-time digital signal processing, which was what we needed for this project specifically. There's a smaller board, which really helped our choice, and then the I/O considerations had multiple input outputs for audio. The microphone we chose was the Comica CVM VM20. We chose this mic for a few reasons. The battery power means that it has no possibility for power coupling, which is very helpful for good audio capture. The main reason we picked it, though, is the cardioid audio capture, which means that it picks up nothing really from the side, only from the front. which is what we wanted for the desired audio capture. We use the Raspberry Pi 3 because it's a widely accessible open source library, and we used it for the GPIO HTTP request integration for the application that Maya and Mustafa wrote. And then we used the Analog Discovery 2 as an oscilloscope to measure the signal delay between the audio input and output of the microcontroller, such that we could space things out correctly to have the correct timing for things.
This will be a demonstration of our frequency detection and cutoff filter for our ANC. Currently it's running at 400 Hertz. It will cut off at 1250. So as we raise the frequency, cuts off. So this will be a demonstration of our volume control using the app on the Android phone through the Pi connected to our microcontroller. Frequency right now playing is at 444 Hertz. So you can hear it from the phone, but you can't hear it from the speakers. And then this will be volume controls. And we can go down as well. This is a simple capture showing the inversion of the frequency using the Analog Discovery kit. Blue is the microphone input, yellow is the microcontroller output. Here we can see that the signal is actually inverted, but it does take 2.67 milliseconds for the signal to actually be inverted and outputted.